Identifying explicit keywords in online text to detect misinformation is a standard engineering pipeline. However, this approach relies on users making explicit claims. It fails to account for a significant blind spot in natural language processing, detecting implicit context. Humans often communicate through storytelling shortcuts, narrative devices called tropes. These are familiar patterns used to convey complex ideas and attitudes without stating them directly. For example, if a text says, "Paul likes Anne, but his friend Harry met her first," a model must infer the love triangle trope. The exact phrase never appears, yet the meaning is clear to a human reader. Online, content producers employ these narrative tropes in short social media posts to activate preconceived biases and simplify complex societal issues. Translating this implicit behavior into a quantifiable machine learning task requires framing it as a multi-label classification problem. In this classification context, a single short text might contain 0, 1, or several overlapping tropes simultaneously. Without a mathematical way to identify these tropes, current NLP pipelines remain blind to the specific way humans construct manipulative narratives online. Solving this requires a choice between two different neural network architectures for detecting context. Modern NLP offers two primary methodologies for this specific task. The first is the massive parameter approach, represented by large language models designed for zero-shot inference across a wide range of general data. This includes ChatGPT 3.5, which utilizes 175 billion parameters, and Llama 3 Instruct, utilizing 8 billion parameters. The second is the domain-specific approach, where smaller models like BERT Large Uncased or COVID TwitterBERT are fine-tuned on a targeted dataset. By analyzing the performance data, we can determine whether domain-specific fine-tuning or sheer parameter count is more effective at decoding human tropes. The outcome of this test defines the stakes for ML engineers. It will show whether abstract narrative detection can be solved with more compute, or if it requires targeted architectural intent. Before testing these architectures, researchers had to establish the first ground truth dataset for online tropes. They collected 3,300 English-language Twitter posts centered on the highly debated topics of vaccines and immigration. These posts were selected strictly by keyword, with no pre-filtering for misinformation or factual accuracy. Transforming these raw tweets into training data required a four-phase qualitative coding process: familiarization, open coding, framework development, and verification. To protect the integrity of the data, human annotators labeled any text where a trope was not clearly evident as none. This process successfully isolated 9 distinct, recurring trope labels across the collection of posts. Because human discourse is often layered, individual texts could be assigned multiple labels simultaneously. This meticulously annotated baseline makes it possible to mathematically evaluate an AI's ability to detect unstated narrative intent. For the benchmark test, the fine-tuned models were trained on 80% of the dataset, while the large language models operated zero-shot. The models were evaluated using the F1 score, which measures the balance between precision and recall across all 9 trope categories. The zero-shot LLMs provided baseline performance metrics on the validation set. When fine-tuned models were put to the same test, their scores reached significantly higher than the massive LLMs. COVID BERT FT achieved the highest weighted average F1 score of 0.65, more than doubling the performance of ChatGPT 3.5. Pre-training specifically on COVID-related tweets gave this model a distinct contextual advantage when evaluating the vaccine-heavy segments of the data. This performance comes despite a significant parameter gap. COVID BERT FT outperformed a model over 500 times its size. When parsing implicit cultural narratives, a smaller model trained on specific domain language proved more effective than a generalized system. To understand why models with billions of parameters struggled with these narrative concepts, we have to examine the zero-shot failure mechanics. LLMs show high sensitivity to prompt phrasing and hyperparameter settings, which leads to inconsistent labeling. This sensitivity often leads to false positives, where the model hallucinates the presence of a trope in a text where none exists. However, even the fine-tuned models showed high variance in performance across the 9 different trope categories. While tropes like liberty, freedom were identified accurately, the models consistently failed to detect the time proves me right trope. High-performing tropes contained consistent, recurring bigrams, such as experimental vaccine, which provide the model with a clear statistical signal. In contrast, low-performing tropes suffered from extreme feature sparsity. They lacked distinct n-gram markers, leaving the model with no statistical pattern to follow. This sparsity was likely aggravated by a small sample size, as the time proves me right trope only appeared in 2.3% of the training examples. A model's ability to quantify human storytelling is limited by the density of these statistical markers, regardless of the model's overall size or conceptual breadth. These findings have direct implications for the design of automated fact-checking pipelines. A common assumption in moderation is that detecting known persuasion techniques or conspiracy theories will capture most bad faith content. To test this, researchers ran established conspiracy detection and persuasion technique models over the tropes dataset. The data revealed a lack of statistical intersection. The use of a trope does not necessarily correlate with the use of a known conspiracy or persuasion technique. This heat map displays Pearson correlation coefficients between the tropes, providing mathematical evidence of their narrative independence. The dark purple squares indicate Matthews correlation coefficients of less than 0.07. This shows that a text employing a trope like hidden motives is not inherently spreading a conspiracy theory. Tropes operate on a mathematically distinct vector. They are a unique tool for communication, rather than a proxy for misinformation. To ensure the success of COVID-BERT-FT wasn't just a result of overfitting to the training data, researchers conducted an out-of-distribution test. The model was tasked with identifying tropes in an entirely separate dataset of 2,000 tweets related to conspiracy theories. When evaluating high-confidence labels in this unseen data, the model achieved a binary F1 score of 0.943. This result suggests that fine-tuned trope detection models maintain high accuracy even when applied to data outside their original training distribution. While themes define the central message of a text, tropes provide the structural shortcuts humans use to deliver that message. Incorporating fine-tuned trope detection alongside standard fact-checking nodes addresses a major blind spot in current moderation systems. By quantifying the implicit, engineers can map a previously unrecorded layer of narrative intelligence, changing the accuracy with which machines categorize human discourse.